Welcome back. In the first part of our conversation, we explored how your curiosity about robotics, software, and intelligent systems eventually led you into physical AI engineering. Now, I'd like to ask something that many learners wonder about. What is the reality of working in physical AI that textbooks don't prepare you for?
That's a great question. Many people imagine physical AI as building an intelligent robot, writing a machine learning model, and watching it perform tasks perfectly. The reality is much more complex and much more rewarding. Building a physical AI system isn't about teaching a machine to think, it's about teaching a machine to perceive, understand, decide, and act in an unpredictable physical world. Unlike software running on a computer, intelligent machines must deal with changing lighting, moving objects, noisy sensors, uneven surfaces, unexpected obstacles, and constantly changing environments. That makes physical AI one of the most multidisciplinary fields in engineering.
So, the real challenge isn't just artificial intelligence, it's understanding the environment too.
Exactly. A machine can only make good decisions if it first understands what's happening around it. Imagine asking someone to walk through a crowded room while blindfolded. Even if they're intelligent, they can't move safely because they can't perceive the environment. Physical AI works the same way. Perception always comes before intelligence. That's why cameras, LiDAR, radar, depth sensors, microphones, force sensors, GPS, and inertial measurement units, IMS, are so important. They're the machine's senses.
Many beginners hear terms like computer vision and sensor fusion very early. How do they fit into physical AI?
Let's imagine an autonomous delivery robot. A camera identifies pedestrians and traffic signs. LiDAR measures distances. An IMU detects movement and orientation. GPS estimates location. Wheel encoders measure how far the robot has traveled. Each sensor contributes useful information, but none of them is perfect on its own. Computer vision allows the robot to understand what it sees. Sensor fusion combines information from multiple sensors into a much more reliable understanding of the environment. It's similar to how humans use sight, hearing, and balance together while walking. Multiple senses working together create better decisions.
That's a great analogy. Many learners also hear about machine learning and deep learning. Are they always necessary?
Not always. Machine learning helps systems recognize patterns from data. Deep learning is particularly useful for tasks like image recognition, object detection, speech understanding, and complex perception. But not every problem requires deep learning. Sometimes traditional control systems, rule based logic, or classical robotics algorithms provide better solutions. One of the biggest misconceptions is believing AI is the answer to every engineering challenge. Good engineers choose the right tool for the problem, not the newest one.
Another topic that sounds exciting is reinforcement learning. How would you explain it?
Imagine teaching a child to ride a bicycle. You don't give them hundreds of equations. Instead, they try, they make mistakes, they adjust. Gradually, they improve. Reinforcement learning works similarly. An intelligent agent learns through experience. It receives rewards for good decisions and penalties for poor ones. Over time, it discovers strategies that maximize success. In physical AI, reinforcement learning is used for robot manipulation, autonomous navigation, motion planning, and decision making in dynamic environments. However, we usually train these systems inside simulations before allowing them to operate in the real world,
Why simulations? Why not simply train robots directly?
because mistakes in the real world can be expensive or dangerous. Imagine teaching a warehouse robot to navigate entirely through trial and error. It might collide with shelves, damage products, or create safety risks. Instead, engineers build realistic simulation environments. The robot practices thousands or even millions of scenarios safely inside the simulator. Once it performs reliably, we transfer that knowledge to the real machine. That's why simulation and digital twins have become essential parts of modern physical AI development.
Many people think robots rely entirely on cloud computing. Is that true?
Only partly. Some processing happens in the cloud, but many decisions must happen immediately. Imagine a robot arm avoiding a collision. Waiting for instructions from a distant cloud server would introduce unnecessary delays. Instead, many physical AI systems use embedded AI and edge intelligence. AI models run directly on embedded computers installed inside the robot. This allows decisions to happen within milliseconds, while the cloud handles tasks like fleet management, long-term analytics, and model updates. Cloud and edge complement each other.
That sounds similar to how humans make decisions. Some actions are immediate, while others involve long term planning.
Exactly. Physical AI often follows the same principle. Immediate reactions happen locally, long-term learning and optimization happen elsewhere. That's why embedded AI has become so important.
Another fascinating topic is human robot interaction, or HRI. Why has it become such an important area?
Because robots increasingly work alongside people rather than replacing them. In modern factories, collaborative robots or cobots share workspaces with human operators. Healthcare robots assist doctors and nurses. Warehouse robots support logistics teams. Service robots interact directly with customers. Building these systems isn't only about movement, it's about communication. Robots must understand human intentions. People must understand robot behavior. Trust becomes just as important as technology. That's why human robot interaction combines robotics, psychology, design, ergonomics, and artificial intelligence.
Safety must also be a major concern.
Absolutely. Traditional software errors might display an incorrect message. Physical AI errors can have real world consequences. Imagine an autonomous forklift misunderstanding its surroundings, or a surgical robot making an incorrect movement. Safety isn't something we add after development, it's designed into the system from the very beginning. Engineers continuously test perception systems, emergency stopping mechanisms, collision avoidance, fail-safe behaviors, and recovery procedures. Reliability is just as important as intelligence.
We've talked about intelligent robots. How does physical AI contribute to modern industries?
Almost every industry is adopting physical AI. Manufacturing uses intelligent robots for assembly and quality inspection. Logistics uses autonomous mobile robots for inventory movement. Agriculture uses AI-powered robots to monitor crops and automate harvesting. Healthcare uses intelligent systems for surgery and patient assistance. Mining uses autonomous vehicles in hazardous environments. Construction uses robots for inspection and repetitive tasks. Energy companies use drones for infrastructure monitoring. The common goal is the same: helping people perform work more safely, efficiently, and consistently.
Before we conclude this segment, if there is one lesson every future physical AI engineer should remember, what would it be?
Don't think of artificial intelligence, robotics, computer vision, machine learning, reinforcement learning, embedded AI, human robot interaction, and digital twins as separate subjects. Think of them as building blocks of one intelligent system. Sensors allow machines to perceive. Computer vision helps them understand. Machine learning recognizes patterns. Reinforcement learning improves decisions. Embedded AI enables real-time intelligence. Simulation prepares systems safely. Human-robot interaction enables collaboration. Safety ensures trust. When these technologies work together, machines become capable of solving meaningful real-world problems.
That's a fantastic perspective. Today's discussion has shown us that physical AI isn't simply about building smarter robots. It's about creating intelligent systems that can safely perceive, understand, decide, and act in the real world. In our next segment, we'll hear real engineering stories. We'll discuss robots that behaved unexpectedly, perception systems that almost failed, difficult deployments, surprising engineering mistakes, challenging customers, and the valuable lessons that only experience can teach. Stay with us.